Ancient conceptions of the sun. The sun, as the source of light and life, has always captivated human attention, and its mystery remained an object of worship and study throughout the history of mankind. Even in ancient times, people sought an explanation for this majestic celestial body, and over thousands of years, ideas about the sun evolved, from mythological representations to the first attempts at scientific explanation. Ancient civilizations personified the sun, linking it to deities, and later, philosophers and astronomers attempted to reveal its natural laws. The role of the sun in the mythology and religions of ancient civilizations. In antiquity, the sun was perceived not only as a celestial body but also as a symbol of life, strength, and divine origin. In many cultures, the sun was at the center of mythological beliefs, embodying a god or divine entity that bestowed light and warmth to all living things. Each culture had its unique myths and beliefs related to the sun. Ancient Egypt, one of the earliest civilizations, regarded the sun as a crucial symbol. The main sun god was Ra, the god of sunlight and the creator of the world. According to Egyptian mythology, every day Ra sailed across the sky in his solar boat, and at night, he descended into the underworld to fight evil. The symbolism of the sun god was central to Egypt's religious life, and the cult of Ra profoundly influenced Egyptian culture and architecture, including the construction of pyramids aligned with the solar cycle. In Mesopotamia, the sun also had divine significance, and the primary sun gods were Shamash in Mesopotamia and Asho in Assyria. Shamash was the god of justice who illuminated the earth with his light daily and, according to beliefs, helped people make righteous decisions. This god was revered in both Assyrian and Babylonian civilizations. In ancient Greece, the sun was associated with the god Helios, who drove his chariot across the sky pulled by 4 fiery horses. Helios was the personification of the sun itself, and his journey across the sky symbolized the day replacing the night. His cult was also closely related to prophecy, and Helios was considered a witness to all events on Earth. However, later the image of Helios was replaced by the philosophical concept of the sun as a celestial body. In ancient Rome, the sun's cult was also highly developed, and the god Sol was worshipped as the celestial body embodying power, strength, and immortality. With the rise of the Roman Empire, the sun cult acquired political significance, and Emperor Alexander Severus even established a day dedicated to the sun as an official holiday. In Rome, there was also a connection between the sun and the emperor, who was perceived as its earthly embodiment. Thus, in the myths and religions of ancient civilizations, the sun not only symbolized life but also became an important cultural and political symbol, linking people to the divine. Ancient Greek and Roman theories about the sun. The first philosophical and scientific theories about the sun emerged in ancient Greece and Rome. By the 4th century BCE, thinkers began to hypothesize that the sun was not a deity but a celestial body somehow related to Earth. These early scientific attempts to explain the nature of the sun marked an important step in the development of astronomy. One of the first philosophers who attempted to explain the nature of the sun was Anaximander. He proposed a theory in which Earth floats in space without visible support and has no center. Anaximander also hypothesized that the sun, like other celestial bodies, revolves around the Earth. Although his model was far from modern scientific understanding, it opened the door to further research. The next step was the teachings of Pythagoras and his followers, who began to consider the sun as a fiery body, not related to Earth, but moving along a celestial circle. This revolutionary idea gradually led to the realization that the sun was not part of the Earth's atmosphere, but was an independent object in space. However, the most significant contribution to theories about the sun came from Aristotle. He proposed a model in which Earth was at the center of the universe, and all celestial bodies, including the sun, revolved around it. In his philosophical system, the sun and other planets moved along perfect spheres that represented ideal and unchanging forms, perfectly matching the nature of celestial bodies. This geocentric model dominated astronomy for over 2,000 years until it was overturned by the heliocentric theory. In ancient Rome, the idea of the sun as an important celestial body was continued by philosophers like Ptolemy. Ptolemy developed a more detailed geocentric model in which he represented the Sun as one of the planets orbiting around the Earth. His theory was accepted as true for many centuries and formed the basis of medieval astronomy. The first attempts at scientific explanation of the nature of the Sun, Aristotle, Ptolemy. Despite attempts by philosophers to regard the Sun as a physical phenomenon, their explanations remained limited. Aristotle, for example, argued that the Sun was a celestial body located within one of the spheres of the universe, revolving around Earth. His model could not explain many observable phenomena, such as the movement of the Sun across the celestial sphere and changes in its position. Ptolemy continued to develop the geocentric model, proposing a more complex system with eccentric orbits to describe the movements of the Sun and other planets. His theory asserted that all planets moved along circles, but with some deviations, epicycles, which allowed for more accurate predictions of their motion. Ptolemy was confident that Earth was the center of the universe and that the Sun, as one of the planets, orbited around it. Although these models dominated for centuries, they could not explain all aspects of the observed movement of the Sun. Only with the development of astronomy during the Renaissance, and with the work of Copernicus, Galileo, and Kepler, did it become clear that Earth was not the center of the universe and that the Sun was the object around which the planets revolved. Geocentric versus heliocentric system. One of the most important steps in astronomy was the acceptance of the theory that it was not Earth that was at the center of the universe, but the Sun. This revolutionary idea was proposed in the 16th century by the Polish astronomer Nicolaus Copernicus, who introduced the heliocentric system. In his model, the Sun was at the center of the solar system, and Earth and other planets revolved around it. The heliocentric theory was based on observations that showed the movement of planets made more sense if the Sun was considered the center of their orbits. However, at that time, this theory was radical and met strong opposition from supporters of the geocentric model, particularly from the Catholic Church. Galileo's work with the telescope and observations by Johannes Kepler, who discovered the laws of planetary motion, ultimately confirmed the correctness of the heliocentric model. This marked a turning point in science, and with this discovery, the understanding of the nature of the Sun and its role in the solar system changed significantly. Thus, ancient conceptions of the Sun evolved from mythological explanations to the first scientific theories. These ideas laid the foundation for further astronomical research and opened the way for a more accurate understanding of what the Sun is and how it is connected to Earth and the other planets. The era of Copernicus, Galileo, and Kepler. The 16th to 17th centuries marked a crucial stage in the development of astronomy, when scientific discoveries made by Nicolaus Copernicus, Galileo Galilei, and Johannes Kepler radically changed the understanding of the universe, the Sun, and its place within it. These discoveries initiated the astronomical revolution, which transformed the foundations of science and philosophy and heralded a series of discoveries to be made in the following centuries. During this period, myths and religious dogmas gave way to scientific theories, allowing people to understand the true position of Earth and the Sun in the cosmos. Copernicus and the revolution of the heliocentric model. The Polish astronomer Nicolaus Copernicus is considered the founder of the scientific revolution in astronomy, with his name forever associated with the shift from the geocentric model of the world to the heliocentric one. In 1543, when Copernicus published his famous book on the revolutions of the heavenly spheres, he challenged the millennia-old tradition that held Earth at the center of the universe. In his theory, Copernicus argued that the Sun, not the Earth, was at the center of the solar system, and that the Earth, rotating on its axis, simultaneously moved around the Sun. Copernicus' heliocentric model was based on several important observations. He noted that the movements of planets, particularly those of Mars and Venus, could be more accurately described if they were assumed to rotate around the Sun, rather than Earth. The models based on geocentrism could not explain phenomena such as retrograde motion of planets. The heliocentric system, on the other hand, offered a simple and elegant explanation. However, at the time, Copernicus' work did not receive immediate widespread scientific recognition. His hypothesis contradicted the prevailing views, which were based on biblical texts and Aristotle's philosophy. It was believed that the Earth was the immovable center of the universe and that all celestial bodies revolved around it. For decades, the heliocentric theory was harshly criticized by both the Catholic Church and most scientists. Nevertheless, Copernicus did not dispute the physical reality of the cosmos. Rather, he proposed a new mathematical model that more accurately described the observed movements of celestial bodies. His work ultimately provided a powerful impetus for the development of astronomy in future centuries. Galileo and his telescopic observations of sunspots. When the telescope was invented at the beginning of the 17th century, the ability to make more accurate observations opened new horizons for astronomy. One of the first astronomers to use the telescope for observing celestial bodies was the Italian scientist Galileo Galilei. In 1609, Galileo improved the telescope and began conducting observations that would change our understanding of the cosmos. One of Galileo's most significant contributions to astronomy was the discovery that the Sun was not a perfect celestial body, as had previously been believed, but had sunspots on its surface. In 1610, Galileo observed dark spots on the Sun's surface and, through his observations, proved that these spots were not atmospheric phenomena but actual objects on the Sun. These sunspots were signs of solar activity, which would later be studied in detail by scientists. Galileo also discovered the phases of Venus, which provided further confirmation of Copernicus' heliocentric theory. Galileo's observations showed that Venus, like other planets, moved in orbit around the Sun, once again proving that the Sun, not Earth, was the center of the solar system. It is important to note that Galileo faced persecution by the Catholic Church. His support of the heliocentric model provoked strong protests, and in 1632, after the publication of his book Dialogue concerning the two chief world systems, Galileo was condemned by the Inquisition for heretical views. He was forced to recant his scientific beliefs, but his discoveries continued to inspire generations of scientists. Johannes Kepler and the laws of planetary motion. The next step in the development of astronomy after Galileo was taken by Johannes Kepler, a German astronomer whose work ultimately confirmed the heliocentric model and laid the foundations of modern astronomy. Kepler, a mathematician and astronomer, worked to more accurately describe the motion of the planets. Kepler became famous for his three laws of planetary motion, which had a revolutionary impact on the understanding of the nature of planetary orbits. Kepler's first law asserts that the orbits of planets are ellipses, not circles, as previously believed. This law overturned the centuries-old idea that planets moved in perfect circular orbits. Kepler's second law, also known as the law of equal areas, explains that the line connecting a planet to the Sun sweeps out equal areas in equal times. Kepler's third law links the orbital periods of planets to their distance from the Sun. The farther a planet is from the Sun, the longer its orbital period. These laws became the foundation for understanding planetary motion and played a vital role in the further development of astronomy. By studying the observations of Tycho Brahe, Kepler used precise data about the positions of planets to mathematically prove the laws of their motion. His work helped to definitively confirm the heliocentric model and dispel the old geocentric theories. How these discoveries changed our view of the Sun. The discoveries of Copernicus, Galileo, and Kepler significantly changed the perception of the Sun and its role in the cosmos. Before these discoveries, the Sun was viewed not only as a source of light and life but also as an essential element connected to Earth and its immobility at the center of the universe. The geocentric model asserted that Earth and the Sun held a special place in the cosmos, with other planets and celestial bodies subordinated to their movements. With the shift to the heliocentric model, the Sun was placed at the center of the solar system, and its role as the stable and primary source of light and energy became clear. Galileo's discoveries, particularly his observations of sunspots, showed that the Sun was not a perfect celestial body, but a complex and evolving star with its own features and dynamics. Kepler's laws finally dispelled myths about perfect and unchanging orbits, showing that the motion of planets was not the result of mystical or divine forces but followed clear mathematical laws. These ideas began to change the view of the Sun as part of a broader cosmic system and laid the foundation for future scientific discoveries in astronomy. Thus, the discoveries of the Copernican, Galileo, and Kepler eras not only changed the understanding of the Sun but also created the basis for further exploration of the cosmos, which began to unfold to humanity with each new step in scientific thought. Modern astronomy and the study of the Sun. The study of the Sun is an integral part of modern astronomy, and over the past few centuries, we have made tremendous strides in understanding the nature of this celestial body. From the early observations using telescopes to space missions that have allowed us to explore the Sun from close distances, scientific discoveries have transformed our view of the Sun as a star, as well as its influence on Earth and the other planets in the solar system. Modern astronomy employs various methods, including spectroscopy, the study of sunspots, the solar wind, and the investigation of the Sun's internal structure. All these studies allow scientists to more accurately explain the processes occurring on the Sun and predict its impact on our planet. Spectroscopy and the discovery of the Sun's chemical composition. One of the key achievements of modern astronomy is the use of spectroscopy to analyze the chemical composition of the Sun. Spectroscopy is a method of studying light that allows scientists to break it down into its constituent colors, or spectrum. Each element that makes up the Sun absorbs and emits light at specific wavelengths, producing characteristic spectral lines. This discovery became possible thanks to the work of scientists like Heinrich Hertz and Gustav Kirchhoff, who, in the 19th century, first began applying spectroscopy to analyze starlight. Applying this method to the Sun revealed that it is primarily composed of hydrogen and helium, with small amounts of heavier elements such as oxygen, carbon, neon, and others. One of the most notable examples of spectroscopy was Harold W. Shapley's discovery in 1915. He used spectroscopy to study solar flares and their effects on Earth's atmosphere. Spectroscopy also made it possible not only to study the Sun's chemical composition but also to measure the temperature of various layers of its atmosphere. For example, the temperature of the Sun's photosphere is about 6,000 Kelvin, while the temperature in the corona can reach millions of degrees, which is strikingly different from the temperature at the Sun's center. Today, using spectroscopy, scientists can also investigate the solar wind flows, which are the result of solar activity and can significantly affect Earth's magnetosphere. The role of sunspots and solar activity. One of the most noticeable manifestations of solar activity is sunspots, dark areas on the Sun's surface that are cooler than the surrounding photosphere. These spots are related to the Sun's magnetic fields and serve as an important indicator of solar activity. The first observation of sunspots was made by Galileo in 1610. However, with the advancement of astronomy and observational technology, scientists realized that sunspots are not random formations but exhibit cyclic behavior. Every 11 years, the Sun experiences a solar activity maximum, when the number of sunspots peaks, and a minimum when there are almost no sunspots. This solar activity cycle, known as the solar cycle, affects conditions in the solar system, including its impact on Earth. Sunspots are directly related to larger solar phenomena such as solar flares and coronal mass ejections, CMEs. Solar flares are powerful bursts of radiation that can impact Earth and other planets, disrupting their magnetospheres, causing auroras, and in some cases, affecting satellite and radio systems. CMEs are plasma eruptions from the Sun that can travel through space and collide with Earth's magnetosphere, causing geomagnetic storms that can affect technological systems, including satellite communications, navigation, and even power grids. Studying sunspots helps scientists predict solar activity and understand the mechanisms behind these phenomena. This is important not only for science but also for practical applications, such as protecting satellites and infrastructure from solar storms. The discovery of the solar wind and its impact on Earth. One of the most important discoveries of the 20th century was the discovery of the solar wind, a flow of charged particles that emanates from the Sun and spreads throughout the solar system. This discovery was made in the 1950s with the help of space probes, and it marked a turning point in astronomy as well as in the study of interactions between the Sun and the planets. The solar wind consists mainly of protons and electrons, and its speed can reach several hundred kilometers per second. It affects Earth by creating a magnetosphere that protects the planet from charged particles and regulates climate processes. However, despite this protection, the solar wind can induce geomagnetic storms, which may be hazardous to satellites, navigation systems, and even energy infrastructure. Particularly intense geomagnetic storms caused by the solar wind can affect power grids, disrupt radio communication and navigation systems, and even damage satellites. The study of the solar wind has become an important part of modern space weather forecasting, and scientists are working on methods to protect against solar storms to minimize their impact on Earth's technologies. The theory of the Sun's internal structure. Solar physics also includes the study of the Sun's internal structure, which until recently remained one of the most complex challenges for astronomers. The internal structure of the Sun determines how it emits light and energy, which in turn affects Earth's climate and life on the planet. The Sun consists of several layers: the core, radiative zone, convective zone, and the atmosphere, which includes the photosphere, chromosphere, and corona. The energy of the Sun is generated at its center through nuclear fusion, where hydrogen is converted into helium, releasing vast amounts of energy. This process is called thermonuclear fusion, and it is the primary source of light and heat that we receive from the Sun. One of the most important aspects that scientists have sought to understand is how energy is transferred from the Sun's core to its surface. In the Sun's radiative zone, energy moves through the process of radiative transfer, where photons are absorbed and emitted at various points in this zone. This process takes thousands of years for energy to reach the convective zone, where it begins to move more rapidly through convection currents. Modern methods, such as helioseismology, allow scientists to study the Sun's internal structure by analyzing waves that travel through its layers. Helioseismology helps to understand the processes that govern solar activity and energy, and also helps predict how the Sun will behave in the future. XXXXI centuries, new technologies and missions to the Sun. The 20th and 21st centuries have been a time of significant achievements in the fields of astronomy and solar physics, thanks in part to advances in technology and research missions aimed at studying the Sun. With the development of telescopes, satellites, and new data processing methods, scientists have been able to uncover many of the secrets of our star, leading to important discoveries in heliophysics. The launch of satellites such as SOHO, Solar and Heliospheric Observatory, and Parker Solar Probe, along with studies of solar flares and coronal mass ejections, CMEs, has greatly expanded our knowledge of solar activity and its impact on Earth and space as a whole. Launch of the first satellites for studying the Sun, SOHO, Parker Solar Probe. Key events in solar research over the past few decades have been the launches of space probes specifically designed for studying the Sun. One of these satellites was SOHO, which was launched into orbit in 1995. SOHO became a joint mission between the European Space Agency, ESA, and NASA, and turned out to be one of the most successful and long-running satellites in the field of solar astronomy. SOHO was designed to study the solar atmosphere, sunspots, solar wind, and their interactions with Earth. The satellite allowed scientists to observe the Sun with unprecedented precision and to study solar activity in real time. One of the most significant discoveries of the SOHO mission was the observation of solar flares and coronal mass ejections, as well as a detailed study of the solar wind and its influence on Earth. SOHO was the first satellite that enabled us to see and examine how solar activity affects our planet, opening new horizons in our understanding of solar physics. In addition, SOHO played a crucial role in developing the theory of solar wind and helped establish that the Sun emits streams of charged particles that affect Earth's atmosphere and magnetic field. In 2018, a more ambitious satellite, Parker Solar Probe, was launched. It became the first spacecraft to approach the Sun at a record-breaking close distance. The main mission objective was to study the solar corona, investigate the origin of the solar wind, and examine the mechanisms behind strong solar flares and coronal mass ejections. Parker Solar Probe was launched with the aim of directly observing processes occurring in the hottest and most puzzling areas of the solar atmosphere and understanding the triggers behind such phenomena. One of Parker Solar Probe's greatest achievements was that it made several historic approaches to the Sun, enabling scientists to gather unique data on the solar wind and solar activity. This probe has opened new perspectives for studying the nature of the Sun and solar flares, as well as analyzing how these events might impact conditions on Earth and space technologies. Development of heliophysics and the study of solar cycles. Heliophysics is the study of the Sun, its influence on the solar system, and its interaction with the interstellar medium. The development of heliophysics has been an important milestone in astronomy and solar physics in the 20th and 21st centuries. Research on solar activity, solar cycles, and solar wind are key to understanding how the Sun interacts with our planet and other objects in the solar system. Solar cycles are periodic changes in solar activity related to the number of sunspots and the intensity of solar flares. These cycles play an important role in solar research because they significantly influence geophysical processes on Earth and affect various cosmic bodies. Heliophysics aims to create models that help predict solar activity and its consequences for our planet. To date, scientists have been able to study solar cycles more accurately and establish their connection to changes in solar activity. The duration of solar cycles is about 11 years, and each cycle has periods of high and low solar activity. These cycles play an important role in the impact of solar wind and solar flares on Earth. Based on data gathered from satellites and other instruments, astronomers are developing models that help predict solar storms and their consequences for Earth. This knowledge is important for protecting satellite systems, navigation, and other technologies that may be vulnerable to solar activity. Discoveries in solar flares and coronal mass ejections. Solar flares and coronal mass ejections, CMEs, are among the most powerful and destructive phenomena on the Sun. These events can cause significant changes in space, affecting Earth and other planets in the solar system. Solar flares are intense bursts of electromagnetic energy that occur on the Sun, while CMEs are expulsions of charged particles from the solar corona into space. Solar flares can affect Earth's atmosphere and technological systems, causing geomagnetic storms, disrupting satellite operations, and complicating radio communications. Coronal mass ejections can affect the entire solar system, including spacecraft, and cause damage to them. Research on solar flares and CMEs has become an important part of missions such as SOHO and Parker Solar Probe, as well as other satellites and space probes. These missions have provided new data on the mechanisms behind solar eruptions. For example, observations made with SOHO allowed scientists to be the first to see how solar particles are ejected and what causes such powerful events. Most recently, in 2020, the Parker Solar Probe mission was able to approach the Sun so closely that it discovered surprising data about how solar flares charge up and become so powerful. This discovery has been an important step in understanding the nature of solar eruptions and their impact on Earth and other planets. Impact of solar activity on space and Earth technologies. Solar activity has a significant impact on Earth and our technologies. Solar flares and coronal mass ejections can disrupt satellite operations, damage communication and navigation systems, and pose a threat to astronauts in space. Therefore, understanding solar cycles, sunspots, and solar flares is crucial for protecting Earth technologies and advancing space infrastructure. Solar storms can cause geomagnetic storms, phenomena that result from the collision of solar wind with Earth's magnetic field. These storms can lead to satellite outages, navigation system disruptions, and even damage to power lines and infrastructure. As a result, scientists and engineers are developing methods to predict solar storms and protect satellites from the impact of solar wind. Additionally, solar storms can affect radio communications by creating interference in radio frequencies and complicating long-distance communications. This is particularly important for maritime, aviation, and military communications. From a scientific standpoint, understanding solar activity and its impact on Earth is essential for forecasting changes in the space environment and the effects of solar phenomena on global climate. For instance, solar flares can influence Earth's ozone layer, altering climatic conditions on the planet. The 20th and 21st centuries have been a time of unprecedented achievements in the study of the Sun and solar activity. The development of new technologies, such as the launch of the SOHO and Parker solar probe satellites, has greatly improved our understanding of how the Sun influences Earth and other planets. These missions have allowed scientists to uncover many mysteries of solar activity, such as solar flares, coronal mass ejections, and solar wind, and to create models that help predict their effects on our planet. With each new discovery, scientists are getting closer to understanding how our star works and the influence it has on us and our world. Modern missions and research, such as the Parker Solar Probe mission, will continue to open new horizons in solar physics, enabling humanity to better prepare for solar storms and their consequences for space and Earth technologies. The future of solar research and its evolution. The Sun, our closest star, has been the subject of fascination for centuries. Throughout history, human understanding of the Sun has evolved from mythological explanations to sophisticated scientific theories. As we continue to study the Sun with modern technology and advanced space missions, we are uncovering not only how it influences life on Earth, but also its ultimate fate in the distant future. In this section, we will explore the future of solar research and the evolution of the Sun, including how it will change over billions of years, the potential catastrophic scenarios for Earth, upcoming missions to the Sun, and how solar activity might affect the future of humanity. How will the Sun change over billions of years? The Sun, like all stars, is undergoing constant changes. It is currently in the middle of its life cycle, residing in what is called the main sequence phase, during which it fuses hydrogen into helium in its core, producing the energy that sustains life on Earth. The Sun is expected to remain in this stable phase for a few billion more years, but eventually, its hydrogen supply will begin to dwindle, and its behavior will change dramatically. The red giant phase. As the Sun exhausts its hydrogen fuel in the core will contract and heat up, while the outer layers will expand. This will cause the Sun to become a red giant, a phase that will occur in about 5 billion years. During this phase, the Sun will increase in size and luminosity, potentially swallowing the inner planets of the solar system, including Mercury and Venus. Earth, although not likely to be consumed directly, will experience extreme heat as the Sun's outer layers expand. The increased solar radiation will cause the Earth's oceans to evaporate, turning the planet into a scorched, barren world. The helium fusion and planetary nebula. After the Sun becomes a red giant, it will begin to fuse helium in its core, creating heavier elements like carbon and oxygen. This process will occur in pulses, causing the outer layers of the Sun to expand and contract several times. Eventually, the Sun will lose a significant portion of its mass, shedding its outer layers into space in a process known as the planetary nebula phase. This loss of mass will have important consequences for the solar system. As the Sun sheds its outer layers, the gravitational pull on the remaining planets will weaken, causing their orbits to expand. Earth, now a lifeless planet, will be left orbiting a much smaller and cooler Sunday. The Sun itself, after expelling its outer layers, will shrink into a white dwarf. The white dwarf phase. The final phase of the Sun's life will be as a white dwarf, a dense and hot remnant of the star that no longer undergoes nuclear fusion. Over the course of billions of years, the white dwarf will cool and fade, eventually becoming a cold, dark black dwarf. This process, however, will take many trillions of years, far longer than the current age of the universe. Potential catastrophic scenarios for Earth. As the Sun evolves, there are several potential catastrophic scenarios for Earth that could drastically alter the future of our planet and the conditions for life. Solar flares and coronal mass ejections, CMEs. Solar flares and CMEs are powerful eruptions of radiation and charged particles from the Sun's surface and outer atmosphere. These events, while common in the Sun's 11-year solar cycle, could become increasingly severe in the future. A major solar flare or CME directed at Earth could have catastrophic effects on our technology-driven world. The intense electromagnetic radiation from such an event could disrupt communication systems, GPS, and power grids, causing widespread technological failures. Furthermore, CMEs could directly damage satellites in orbit, interfere with space missions, and increase radiation exposure for astronauts. In extreme cases, a powerful solar storm could even pose a risk to human health by increasing radiation exposure on Earth's surface. Such an event, if it occurred today, would result in immense economic losses, potentially leading to months or years of recovery. Supermassive solar flares. While solar flares and CMEs are relatively common, the Sun has the potential to produce much larger and more destructive events, known as supermassive solar flares. These flares would release more energy than typical solar flares, with the potential to cause severe geomagnetic storms. Such events could damage power grids and communication systems worldwide, as well as cause widespread radiation exposure. The likelihood of a supermassive solar flare occurring is difficult to predict, but given the Sun's long-term activity, this scenario cannot be entirely ruled out. If such an event were to occur in the future, it would have profound consequences for Earth's technological infrastructure, disrupting everything from power to communication and transportation systems. The end of life of the Sun. While the eventual expansion of the Sun into a red giant is billions of years away, it is still a distant but inevitable event. During the red giant phase, the Sun's expansion will increase its luminosity and heat output significantly, causing Earth to become uninhabitable. As mentioned earlier, the oceans will evaporate, and the atmosphere will be stripped away. This will mark the end of Earth as a habitable planet. Even if life manages to survive for some time through technological means, the overwhelming increase in temperature will eventually render Earth inhospitable. The final destruction of Earth is, however, a distant event. The Sun will eventually shed its outer layers, leaving a white dwarf that will be far smaller and cooler than the star we know today. At that point, the Earth may continue to orbit the remnants of the Sun, but as a lifeless rock, without an atmosphere or the conditions necessary for life. New missions to the Sun and prospects for study. Despite the challenges presented by solar research, technological advancements have allowed scientists to make significant strides in understanding the Sun's behavior, and new missions are being launched to further explore its mysteries. Parker Solar Probe. One of the most ambitious solar missions to date is NASA's Parker Solar Probe, which launched in 2018 with the goal of studying the Sun's outer atmosphere, the corona, and the solar wind. The Parker Solar Probe is the first spacecraft to enter the Sun's corona, and its close approach to the Sun allows it to gather data about solar activity in real time. The mission's data will help scientists better understand the Sun's magnetic fields, the mechanics of solar wind, and how energy is transferred from the Sun's interior to its outer layers. The Parker Solar Probe's data will also allow scientists to study the behavior of solar flares and CMEs, helping to predict space weather events that could affect Earth. By observing the Sun up close, Parker Solar Probe will provide insights into solar phenomena that have been previously impossible to obtain. Solar Orbiter. Another major mission is the European Space Agency's Solar Orbiter, launched in 2020. The Solar Orbiter is designed to study the Sun from a vantage point that is closer than Earth's orbit, offering a unique perspective on solar activity. The spacecraft will study the Sun's magnetic fields, the solar wind, and the solar corona, providing new insights into the Sun's behavior and its impact on the solar system. One of the key scientific goals of the Solar Orbiter mission is to better understand the Sun's cycle of solar activity, including the formation of sunspots and solar flares. The mission will also help scientists explore the Sun's role in shaping the space weather environment around Earth and the other planets. Future solar missions. Looking ahead, there are a variety of future solar missions planned, including proposed projects to study the Sun's interior, its magnetic fields, and how solar activity affects the solar system. These missions will aim to build on the successes of the Parker Solar Probe and Solar Orbiter, continuing to probe the mysteries of solar physics and improving our ability to predict solar activity that could impact Earth. One exciting prospect is the development of spacecraft that could travel even closer to the Sun, possibly even closer than the Parker Solar Probe. By studying the Sun's corona and outer layers at such proximity, these missions could provide the most detailed data yet on the Sun's behavior and its influence on space weather. The impact of solar activity on the future of humanity. As our dependence on technology increases, the impact of solar activity on Earth will become even more significant. Solar storms and flares can damage communication networks, disrupt satellite services, and cause significant economic loss. As we continue to explore the Sun and learn more about its activity, our ability to predict and mitigate the effects of solar phenomena will be critical for ensuring the safety and stability of modern civilization. Solar activity and climate change. There is also growing interest in the relationship between solar activity and Earth's climate. While solar activity is not the primary driver of climate change, it does have a role in influencing Earth's climate system. During periods of high solar activity, the Sun's increased radiation can cause slight changes in Earth's atmospheric conditions. Similarly, periods of low solar activity may have a cooling effect on Earth's climate, as seen during the Little Ice Age of the 17th century. In the future, understanding the role of solar activity in Earth's climate will be essential for predicting long-term climate patterns and preparing for potential changes. As solar energy plays an increasing role in the global energy mix, understanding the Sun's behavior will be crucial for harnessing solar power and ensuring energy security for future generations. Preparing for space weather events. As we become more reliant on satellites for communication, navigation, and weather forecasting, understanding space weather is essential. Solar storms and CMEs pose a significant risk to satellite systems, potentially disrupting communications, navigation, and weather monitoring. Space agencies and governments are working to develop early warning systems that can predict solar storms and allow us to take protective measures in advance. For example, we may be able to adjust satellite orbits, shut down sensitive systems, or shield spacecraft from the effects of solar radiation. In the future, space weather forecasting will become as important as weather forecasting for protecting critical infrastructure and ensuring the safety of astronauts in space. The Sun's future evolution will drastically change the conditions of our solar system, eventually rendering Earth uninhabitable. However, these events are billions of years away, and there is much we can do in the present to prepare for the impact of solar activity on our planet. Through missions like the Parker Solar Probe and Solar Orbiter, we are gaining valuable insights into solar behavior that will help us predict and mitigate the effects of solar storms. As we continue to study the Sun and improve our understanding of solar physics, we will be better equipped to face the challenges that solar activity poses to our technology-driven world and ensure the long-term survival of humanity.